Hello, everyone. I'm pleased to be with you today to present to the International Conference on Mechanical Engineering in beautiful Sydney in Australia. The title of my presentation is The Effect of Glass and Kevlar Fiber Volume Fraction on the Mechanical Properties of Epoxy Composite. Let's start with a brief introduction about composite materials. In recent decades, with the development of technology, more and more multi-purpose and lighter materials are needed in a wide range of industry. So, every year the demand for advanced materials with better performance increases, which aim to meet new requirements or replace existing materials such as metal and others. These efforts have greatly contributed to the development of new polymer matrix composite materials, enabling significant design improvement. The high performance or high functional fibers offer the advantages of high strength and high stiffness. The use of composite material has found wide application in the manufacture of various products, including automotive, aircraft components, structural components, sports equipment, and biomedical devices, due to their excellent structural properties. Now, let me introduce the idea of this research. The shape, type, size, and volume fraction of the matrix and reinforcing material have a significant influence on the mechanical, physical, and chemical properties of composite materials. In this study, therefore, the effect of glass and Kevlar fiber volume fraction on the mechanical properties of epoxy composite was investigated. Understanding the effect of fiber volume fraction on mechanical properties is crucial for optimizing the performance of composite materials in various applications. In this research, different number of layers, total mass of non-impregnated fibers, and reinforcing material were used to create the specimen. As a result of the different number of the layers, we produce specimens with varying thickness and total composite mass. Volume fraction, every time was changed, depends on this parameter. The fiber total mass refers on the sum of aerial weight of the fibers before the epoxy was applied. 3 cases of fiber total mass were used, masses of 2, 3, and 4 kg, with different number of layers, which depends on the aerial weight of the specific material. Specimens of fiberglass and Kevlar were prepared using the vacuum bagging method. We used epoxy resin as the matrix material. The mechanical behavior of the specimen were tested under uniaxial tension and 3-point bending. Specifically, we examined the sample stiffness and strength. Now let's move to the material selection. The composite were prepared by using 2 types of fiberglass and 2 types of Kevlar with different aerial weight, grams per meter square. A woven reinforcement with plane waving at 0 and 19 was used. You can see their thickness in the first table. Epoxy resin was used as the matrix material. We will find some of its characteristics in the second table, like viscosity, hardener, curing time, tensile, compressing, and flexural strength. About the material preparation, to examine the volume fraction of the specimen created by different number of layers for fiber total mass of the non-impregnated fiber, we use 2 types of Kevlar and 2 types of fiberglass. The mass per unit area for fiberglass is 80 at 200 grams per meter square, and for Kevlar is 61 and 117 grams per meter square. 3 different fiber total masses were investigated in this study. For the cases of fiber total mass of 2 and 4 kg, specimens of fiberglass of 200 grams per meter square and Kevlar 170 grams per meter square were prepared. For the case of fiber total mass 3 kilo, all type of composite were used. You can see the laminating structure of specimen about the different number of the layers in the figure below. The yellow color represents the Kevlar and the white blue represent the fiberglass. The table here shows the abbreviation of the sample, the type of material, the aerial weight, the number of layers, and the total mass of the fibers before epoxy was applied. Now let me explain more about the abbreviation, because we will find many times in the next slide. The first two digits of the sample abbreviation correspond to the varying fiber mass, which is 2, 3, or 4 kilo. The number next refers to the aerial weight, and the last number defines the type of the reinforcing material, fiber or Kevlar. About the graph, due to their different mass per unit area, we need different number of layers to prepare the required fiber masses. As a result, each sample had different thickness and different mass when the epoxy was applied. So, the final sample were produced with different volume fraction. The different values of volume fraction are represented by the yellow bullets in the graph. About the sample construction, samples were prepared as sheets with multiple internal layers. A hand layup method was used to construct the specimen. First, reinforcing fibers were uniformly cut into 250 multiple 250 millimeter pieces. The composites were fabricated by using the vacuum bagging method for 1 hour. The samples were then cured at room temperature. Then, the plate of composite material produced by vacuum bagging was machined to produce the sample. Samples for tensile and bending tests were cut to the size according to this standard. 6 samples were prepared for all different cases. All the tests were done at room temperature. Now we are moving to the tensile behavior. To determine the mechanical properties of the composite, tensile tests were conducted on the fiberglass epoxy matrix composite and Kevlar epoxy matrix composite. Figure A shows a typical stress-strain curve obtained by the fiberglass and Kevlar sample. Sample laminated with different number of the layers according to the requested fiber total mass. Kevlar laminate showed slightly higher strength in stress-strain curve than the fiberglass laminate sample. Energy absorption and elongation are shown in figure B. Similar behavior of elongation at break and energy absorption are obtained for fiberglass sample. Now, Kevlar sample have significant higher thickness than the corresponding fiberglass, which it leads to higher elongation at break and thus more energy absorption. The figure here shows the elastic modulus for all samples. In comparison, in cases of fiber total mass of 2 and 4 kilo, show that the sample produced by fiberglass had higher modulus of elasticity comparing with those produced by Kevlar. This is because fiberglass samples have smaller total thickness and lower total weight comparing to Kevlar sample. Fiber total mass of 2 kilo for both material showed higher modulus of elasticity than the sample of 4 kilo. For the sample with fiber total mass of 3 kilo, 4 different combinations were investigated, 2 fiberglass and 2 Kevlar. A comparison between the 2 reinforcing material shows significant difference about stiffness. Sample of 3K ATF and 3K 61K, they have lower weight per fiber and higher number of the layers compared to the other 2 samples. However, because these samples have higher volume fraction, they showed higher module of elasticity. In this figure, we can see the ultimate tensile strength per fiber total mass. The sample produced by Kevlar showed higher tensile strength comparing to those produced by fiberglass. Now, if we compare the different masses, we will see that sample of fiber mass of 3 kilo show the higher tensile strength for both material, fiberglass and Kevlar. It can also be observed that sample of Kevlar have better toughness and ductility than the sample produced by fiberglass. In the other hand, fiberglass samples have lower ductility, but they have higher elastic module in most of the cases. Now we are moving to the bending test. Here we will find two curves of the load displacement of the composite materials with different fiber mass under bending load. The bending strength of the sample was calculated for maximum load and break. Generally, all specimens exhibit initially a linear load increase, followed by a parabolic increase due to local crack initiation and a final failure. As you can see, only the sample 3K ATF showed poorly linear behavior prior to an abrupt failure. The specimen with mass of 2 kilo, which is the blue color in the graph, have the highest displacement and the lowest carried load. The sample 3K ATF and 4K 170K have the highest carried load for sample of fiberglass and Kevlar, respectively. Here we can see a figure shows the bending and tensile strength with all specimens with varying fiber masses. The bending strength of the sample, fiberglass and Kevlar, was distributed in a range of 218 to 510 megapascal. Only the sample 3K ATF was a level of more than 700 megapascal. In a contrast to the tensile strength, sample produced by fiberglass showed higher bending strength for almost all cases. Now, comparing the different materials by their sample, the lowest values of bending strength were observed by the sample of fiber mass of 2 kilo. It can also be seen that fiber mass of 4 kilo had higher tensile strength, but lower bending strength comparing to fiber mass of 2 kilo. Sample with fiber total mass 3 kilo show the highest value for the bending and tensile strength almost in all different cases. Details for the bending and tensile strength to weight ratio in relation to OU fraction are shown in this slide. Analysis of the tensile test result show that sample of 2 kilo have 2 kilo fiber mass reach higher strength to weight ratio compared to the others for both materials. Kevlar sample 2K 170K demonstrates the highest tensile strength to weight ratio. The sample produced by fiberglass showed higher bending strength to weight ratio in all different fibers compared to Kevlar sample. Now, fiber mass 3 kilo exhibit slightly higher bending strength to weight ratio compared with fiber total mass of 2 kilo, while the fiber total mass of 4 kilo show the lowest strength. So let's move. This figure now shows the stiffness to weight ratio in relation of volume fraction. Here, stiffness defines the tensile module of elasticity. Sample of fiber mass 2 kilo showed the highest stiffness to weight ratio for each material, while sample for fiber total mass of 4 kilo demonstrate the lowest values. This is because of the increase of fiber mass and the associated increase of number of the layers play an important role, since the thickness and the total weight of the sample increase as well. Sample with fiber mass 2 kilo have smaller total thickness and lower total weight compared to the red sample, and due to this, less epoxy fraction. Sample produced by fiberglass showed higher stiffness to weight ratio compared to Kevlar for all three fiber masses. Let's move to the final result of this research. The tensile test showed that Kevlar has higher strength than fiberglass for all material combinations and for all different fiber masses. Fiberglass showed better result of their stiffness with higher module of elasticity comparing to Kevlar for the fiber masses 2 and 4 kilo. It can also be observed that sample of Kevlar have better toughness and ductility than the sample produced by fiberglass. On the other hand, sample produced by fiberglass has lower ductility but higher elastic modulus. And now about the bending test. The bending test showed that the sample produced by fiberglass have higher bending strength for all different masses comparing to Kevlar. In addition, the analysis of strength or stiffness to weight ratio showed that the sample of fiber total mass 2 kilo have higher values comparing to masses 3 and 4 kilo. Sample with a smaller number of the layers and lower thickness need less epoxy resin and show higher strength or stiffness to weight ratio. This leads to the conclusion that with decreased fiber volume fraction, which it means higher epoxy fraction, a crack initiation is more possible. This is why the strength to weight ratio drops. Additionally, with increased fiber volume fraction, which it means lower epoxy fraction, the stiffness to weight ratio proves to be higher as expected. As a conclusion, the aspect of varying layers, the fiber properties, the thickness of sample, the mass of fibers, and the total composite mass, in other words, volume fraction, was found to play an important role for the design of a composite with an optimized stiffness or strength to weight ratio. Furthermore, the findings of this research contribute valuable insight to the field of composite material science, potentially leading to the development of stronger and more durable epoxy composite. And finally, by elucidating the relationship between fiber volume fraction and mechanical properties, this research may inform the design and manufacturing processes of composite materials for real-world application.